Okay, for part two of the BIOMEC tutorial, I'm just going to run everyone through the optimization algorithm that it uses, specifically CMA-ES, or Covariant Matrix Adaptation Evolution Strategy, and what loss function it actually uses. I'm also going to run you through the installation and setup of a Singularity Container, and setting up and running the BIOMEC given an input file, and also run you through the CMA-ES outputs that it gives. We're looking at optimization algorithms. We're looking at things that optimize from a range. We'll optimize a range of parameters within a bound set of range and optimize down to a best fit for experimental given data. Now, the CMA-ES algorithm is kind of like trying to get the bullseye on a dartboard, but we just throw 50 darts at a time. So each throw, we throw all 50 of the darts at once. We see which one scored better and which one scored worse, like closer to the bullseye. And then we readjust how we're throwing all these darts. We can basically give it a shot, see what we get, see if they're closer on this way, basically throw a wider range so we get more of an information of where these scores are. This will then see that it's closer to the bullseye here. It will then readjust the mean of the covariance, and then throw another shot, identify the mean is somewhere around here, and then close in on the best fit using all the darts that it's throwing. In this case, the darts that we're throwing are actually simulations or attempts to fit the experimental data using a given loss function. Now, a loss function is basically just a function we tell the computer to compare the experimental data to simulated data. One of the more straightforward ones, and works for DC as well as AC voltammetry, is the total current difference squared method, where we just use a least squares fitting, comparing the experimental data to the simulated data, and then summing that for each point of time. There's also the log likelihood of this. So assuming a experiment has a mean that looks something like that, but the data points are varied with a Gaussian noise of something like that, it assumes that this model assumes that we can identify the mean given by the simulated data and the noise of variance of the standard deviation of the noise sigma here for a simulated thing. And this will become more of use for the Bayesian inference model, where the advantage of this is it can do this for one experimental data set instead of needing multiple experiments. And it just uses the least square comparison here. Now, for our harmonic methods, we have a harmonic percentage method, where you just get a percentage best fit from this term here, and then just average it for all your harmonics here. This is for every point in time or every harmonic. There is also the Bayesian inference version of this, where we collect all the experimental data points, calculate a mean given by this mu exp. And what this does is it calculates, assuming that f of h is this harmonic percentage for every harmonic, it calculates the mean, it calculates how much the experimental data varies from the mean as a percentage. So you'll have -2%, -0.5%, 0.8%, and 0.15 or something like that percent. And it will calculate the percentage difference. It will then calculate a variance or a standard deviation of that given by this value here. And then it basically uses the simulated data to fit the mean of the experimental data, where the noise model is basically the variation of the percentage difference. This is the Bayesian inference version of the harmonic percentage method. It requires multiple experimental data, but it does it all at once, and you don't need to worry about any fitting the noise parameter as well. You can also ignore or include certain harmonics that may not be fitting well to simulated parameters. But again, you need to understand that this will have a flowing effect to your other parameters you fit. But it's a good alternative when you need to look at the harmonics. Generally, this harmonic percentage method works for optimization methods, and all of these work for optimization methods. This works for singular points as well. So what are we doing when we are optimizing? Well, what we do is we basically have a function of loss of a y-axis, but it'll have a global minima, global, and a local minima, local here and here. And what it's doing is it's basically sampling all these parameter spaces like the dartboard analogy, do this, do it all like this, find that the local minima is here, so it moves everything and throws it out again, does it again, finds out that there's a global minima here, and just closes in on this region here to give you the best fit in your parameter space corresponding to the global minima for your loss function. The advantage of CMA-ES is it's highly parallelizable. So all these 50 darts or 20 simulations or whatever have you can all be run on separate CPUs. So as long as you have the CPU threads there, you can run it all on that. You can very easily optimize it to 8 on a supercomputer, 16. I think I can do like 9 on my desktop quite easily enough. You just have to check that it's doing decently well on your computer. And what it ends up giving you is it gives you a best fit as a point value, but it'll also give you the parameter iterations. It will give you basically an optimization for each parameter as it optimizes down, and as it looks like all these will converge, that means you've got a good approximate value of what it is. So all your different parameters will converge down to the value that they are at the local minimum. Next up, I'm just going to show you how to install Singularity, and that should allow you to run everything. I'll also explain the outputs of this. Okay, I've loaded up Ubuntu version of my computer, and just to get the image container running, you have to download this program called Singularity CE. This will build and run the Singularity containers. You just have to click Get Now and then follow it to some documentation, and then this will run you through how to install the most up-to-date version. They're all backwards compatible, so you can run 3.2 version on 3.8, but you can't run version 3.8 on 3.2. Well, containers built on later versions can't be run on previous versions. It works quite well. It's quite easy to install. You might have to download a few other programs to get it running, but once you get this up and running, you can do all of this. So yeah, once that's installed, you just go to the GitHub repo for BIOMEC. This has all the source code here for BIOMEC. You'll also need Git, and just go click copy, go to open a terminal in this file I just have here, and type in git clone, paste the Git repo link here, and this will just download the whole BIOMEC container. There we go. Now we cd into the BIOMEC container, and that should have all the files here. This is the Singularity definition file. This is what you need to run to build it. I'll show you that. But in essence, if you don't want to use Singularity, you just have to install the correct version of all these programs and hope that it all works, specifically Pints and a few other things. It should all be working. If it isn't, again, email me and I'll fix it up. But if you run the Singularity Container, it should be fine. Yeah, and if it doesn't work, just email me the issue. So first we go to, we type in this command, which is sudo singularity build BIOMEC SMG from the Singularity definition file. Just go def. So what this is it gets Singularity to build biomec.simg, which is the container the Singularity container we're building, using the Singularity definition file. So if I just click enter, type in my password, there we go. This will basically just run and build everything, and if it works properly, you should have the biomec.smg file. So I'll just come back once that's finished installing and run everyone through how to use Singularity image and everything. So I'm just going to go into this MECSim input writer and basically just show you what you need to run BIOMEC. So in essence, what BIOMEC is this is just the input file, where this is for MECSim code for running. Basically, the MECSim simulation that I ran you through the last section. This is a connection to all the experimental data that you're going to load into BIOMEC to run. So this just needs to be the experimental data. I think this is all in reference to where BIOMEC is located, so that also has to be things. So whatever file relative to BIOMEC, this will load it. And then all of this is the CMA-ES options here. This is basically command line where we have standard as just a normal thing. We have our loss function here, where this is the harmonic percentage fit, and this is the CMA-ES optimization. So this tells the computer that we want to do optimization. Then we have a number of variables where it's varying, where here we have a sample of just 5, where this is the middle value that we're optimizing from. This is the smallest value we're going to accept, and this is the maximum value we're going to accept. So we've defined all these ranges here in the first 3 letters. We also have whether or not it is log or log scaled or not, log base 10. You can see with log base 10 the K0 parameter. And then here we just have a code relating to the parameters and which repeat line it is on the MECSim file. So 1 would just mean that it's on repeat line 1, and 2 would mean it's on the second line. So on. Next we have scaled variables, where these are variables which we're just scaling one as another. Here we have the second diffusion coefficient scaled from this variable here by a scaling factor of 1. All of these, I could run you through all of this. The general thing is the input writer will, you can see by Singularity Container just building in the background. The input writer file here will just build one for you from queries of questions, but since they're just text file inputs, you can modify them quite easily directly. Main things to be aware of is that the toll x function is basically at what range you want to accept that it's basically found a good fit. Generally we use 0.1, which is just 0.1%, which is equivalent to what? 0.5% of the range, which means we have a pretty good fit here. You can do 5, 25, 0.1 if you want a really quick. Generally, the higher this value, the more it's converged to a point. So the more certain you want of your fit, the higher this value is. Again, the longer it's going to take. With these, generally, you can do it in 4 minutes. You can do it in, it can take anywhere from 4 minutes to an hour, depending on how many simulations. Generally, it takes around 250 simulations to 1,000. You can, again, parallelize a lot of this. So the more you parallelize, the more faster it's going to take. So yeah, we have all of that. Again, we open a terminal here. Open a terminal here. If we type in Python input we will just be run through a bunch of questions on how to answer, fill out these input files. So we just type in CMA-ES, and then it'll query us what logic file we want. Let's just go TCDS. Please input number of parameters to optimize for, and so on. You'll be queried to fill out this and do all this, and it's quite simple. An important thing is the Bayesian TCDS is also the TCDS, but you also optimize for another parameter which it will query you for when doing it. Okay, so now I'm back into BIOMEC. I'm CD into BIOMEC, and now here I am. Here we can see that we've built the Singularity Container here, biomec.simg. I've also quickly built up a input file for CMA-ES, which is here. This has all the parameters for it, the tolex, the initial sigma value, which is your initial range you're throwing of a shotgun. And then, yeah, so to run BIOMEC, all you do is there's two things you can do. The easiest one is just to go ... biomec SIMG, and then to type in the input file name, which for our case is CMA-ES.txt. Now, you can either run this, which I recommend, or you can run, I believe, Singularity run biomec.simg. And if we run this, so either of those work. And what you'll see here is it just creates a output file here where it's got a copy of the input file, and this should get filled in a while. It's currently just loading everything up, so I'll let that just run. Here we go. Initial setup successful, starting CMA-ES with Bayesian experimental harmonic percentage fit objective function, where the objective function is just another word for loss, the loss function. Starting 6 dimensions, seed. And here we go. So each one of these time intervals is a simulation that it's running, and we're running 4 at a time. So there we go, they're just forth printing, and this will just slowly go through and run it. If I quickly get up my new terminal, for use, and all simulations in MECSim, they generally max out the CPU's thread quite a lot. So I recommend not using all of your threads, but probably enough. There's a good balance between it. Here we can see that it's doing batches of 9, so it goes 4, 4, 1. So it's probably wasting a bit of time there because it is one where it just does 1. You could probably bump it up to 5, and that would speed everything up. And it would optimize a lot faster. We have this optimizing for 10. We have this optimizing for 0.01, so this might take a while. I'm just going to cut it to when it does work. Okay, so the CMA-ES is finished. You can tell it's finished because it just, you can't see it. Let me move that over. It finished by saying calculation complete and finished. So that means it's worked. The program has run complete now, or completed. So to see if it's worked, we open the file here, which is the same name as your input file, And then you'll see it's got harmonic plots, convergence plots, and CMA-ES sample experiment. So if we go to the convergence plots, look at all the variables, we can see that it basically just converges down to the same one. So here we can see that it's converged down successfully to resistance to be 0. Diffusion, it's converged down to something that looks about right. Form potential is converged down quite successfully. Electron transfer rate, alpha, and capacity scalar. It also looks like this isn't that hard of an issue because it's converging in like half the iterations. We could probably change the toll x function, speed all this up if we had to do it a few more times. So we go to the harmonic plots and we check the harmonic plots. This is fine, reasonably decent. There's a lot of issues. So it looks like the diffusion, because the simulated data is higher for the lower harmonics and probably lower for the higher harmonics, diffusion's too high. That's generally what that indicates. If we go to, say, the 6th harmonic, we can see that we're using the Gaussian convolutional fitting program, mainly because there is very little ringing on the sides, or it's been mostly removed, which becomes even more apparent in something like the 8th harmonic, where there is very little ringing, and this stuff is just truncated out in the end. Now, other things you'll get with CMA-ES is the sample experimental TXT, which is your input file, your iterations log, which is just all the iterations that were run, as well as an error function. Yeah, an error function. So this is your variable one and your fit value, which is just the error that it's fitting for. So the objective loss function that it uses. Master EMP, which is the simulator of the best fit data with everything put in nice and fine. MECSim output TXT, which is just the voltage time current data for the simulation of the best fit, and then a results file. With results file's main interest here, you can see that it's taken 23 minutes to run. Again, mainly because it just had too high of a accuracy. Yeah, so we could probably drop that down a bit. You probably just got a bit stuck on something. The parameters you need are all here, where it's basically the values that they are, what code they were, and what repeat line they were. So again, the codes are all correspond to other things. Here it's resistance, diffusion, formal potential, K0, alpha, and capacity scalar. The next set of data is basically how much within the range that you provided to it in the MECSim file. These correspond to the range that they're tested in. So as you can see, this basically just optimized to 0. As such, this is negative, as close to -1 as you're going to get, because the lowest value is 1. 5.0, so it's about halfway between the minimum value and the mean value, as 8.13. Half between the median value and the maximum value because it's positive. And so it's 7 to 9. 3.5, so on. So these unscaled fits are basically where they relate to between your minimum value and your maximum value, and so on. So 0 is right bang in the middle, 1 is your max value, and -1 is your min value. Other things are just your CMA output, harmonic percentage best fits, which are important. It tells you how good of a fit it is to all the different harmonics. If using the total current method, these just won't come up, so don't worry about it. And other things are just your mean parameters and standard deviations, which aren't, this is the end covariance that it's optimized down to. The other things are just the number of function evaluations, which is quite a lot, 1,300, which lead to the 23 minutes. And the stopping criteria of the CMA-ES, so what it reached before cancelling. And that's all quite good. Yeah. For my next part, I'm going to explain how Bayesian inference works. I hope from this part you understood how CMA-ES operates and how we apply it to FTACV voltammetry.